Hello everyone, my name is Prakrit Krishna Shrestha. Today I'm going to design math foundation in SAFE 2016 software. This is evaluation version of SAFE 2016, and for this design of math foundation I'm going to take a building model that I had previously modeled and analyzed in ETABS. So first of all, I'd like to show you some of the parameters and the orientation of the columns of the model. I'll show you that in okay. So this is the orientation of our building that we had previously designed. There are 16 columns named as C1, C2 up to C16, and they are spaced as 6 meters each in x-axis and y-axis. And then some of the parameters like safe bearing capacity of the soil is taken as 300 kilonewton per meter square, and allowable settlement is taken as 1 centimeter. So we have taken the loads coming from the superstructure of the building in all these columns, which will be transferred to the mat. I'll show you the loads also. So these are the dead load and live load coming from the superstructure to each columns. You can see for C1 the dead load is 1850 kilonewton and live load is 797.6 kilonewton, and similarly for all the columns from C1 to C8 it's shown here, and for C9 to C16 you can see here the loads are given as follows. And the concrete will take as M40 concrete for the base slab of the footing, and the rebars will take as HYST 500. So some calculations we need to do for this problem. At first we need to calculate the subgrade modulus of the soil. So subgrade modulus will be safe bearing capacity divided by allowable settlement. That means 300 kilonewton per meter square divided by 1 centimeter. Convert 1 centimeter to meter. So you'll get the result as 3 into 10 to the power 4 kilonewton per meter cube as our subgrade modulus. And for the column strip width, we'll take as 0.25 times L1 or L2. Here both L1 and L2 are 18 meters, so we'll do 0.25 into 18 meters, which will come as 4.5 meter. So we shall take it as 4 meter only. Now we'll start the design in SAFE 2016 software. Here I have opened the SAFE 2016. This is just the evaluation version. So let me begin. First we'll open a new model. In this model, the design code we will take as Indian code. So we'll choose as IS 456-2000, and in design preferences we can go to design code is selected as IS 456, and in minimum cover slabs, for the footing slabs the clear cover is assigned as 50 mm. So top cover and both bottom cover are assigned as 50, and preferred size will take as 22 mm bars. Okay, you can fill in the project information here. In units you can see the units assigned. Now in initial model we can go to grid only. So in grid only, as shown in previous model, we could see that there were, you can see here, so there are 6 meters, 6 meters, 18 meters of length we have. So if we put the spacing as 1 meter, a total number of grid lines will be 18 plus one more extra line, that will be 19 number of grid lines. So in X direction I'll keep number of grid line as 19. Similarly in Y direction number of grids will be 19, and we are taking the spacing as 1 meter. Okay, now Our grids has been specified and it's shown in the model. So let's define some of the properties first. We'll define the materials first. Add new material. First we'll define our concrete, M40 concrete. Material type will be concrete, and then here weight per unit volume for concrete is 25 kilonewton per meter cube. Value of modulus of elasticity we have 316 to 2.7. Poisson's ratio is given as 0.2, and coefficient of thermal expansion we have as 0.000005, and shear modulus it's fine here, and compressive strength, since it is M40, will give compressive strength as 40 Newton per mm square. Okay, our concrete has been defined. Now again we'll define our rebar. Material name will give as HYST 500. Material type is a rebar. Here also some changes we need to make, just like weight per unit volume is 77 kilonewton per meter cube for rebar. Modulus of elasticity is 200,000 Newton per mm square, and value of Fy is 500, whereas Fu is 545 Newton per mm square. Okay, our rebar has been defined. Okay, now we need to define our slab. Go to define and slab properties, add new property. We'll give the name as mat footing. Slab material will be M40, which we had just defined, and for now we'll keep the thickness as 800 mm. This is just a trial and error basis. We have kept it as 800. We can decrease or increase afterwards if some of the criteria are not met. Type will be mat. Okay, now we'll define some columns. Go to define and go to column properties. So here, okay, let me remind you that we have two types of two dimension columns here. One column is 500 by 500 and other column is 600 by 600. So we need to define two columns. I have to show you here in the model. Okay, you can see here that column 1's dimension is 500 by 500. Up to column C5 you can see 500 by 500, and C6, C7 is 600 by 600 and 600 by 600 C7. Also in C10 and C11 you can see 600 by 600, and all others are 500 by 500. So that means this C7, C6, C7, C10 and C11 are 600 by 600 and all others are 500 by 500. So let's define all those columns. Add new property. First let's define this column as column 500 by 500, and material will be M40. This will be the dimension 500 by 500. Okay, again another column will be column 600 by 600. Change the material to M40 and the dimension for 600 and 600. Okay, now both of the columns have been defined. Now we need to define the soil properties. Go to define and then go to soil subgrade properties. Here you can modify this soil 1, which has already been given. Go to select soil 1 and go to modify soil property. In the property name soil 1 is fine. You just need to change subgrade modulus, which we had calculated initially. that was 3 times 10 to the power 4, which is also called 3e plus 04 kilonewton per meter cube. Okay, now we need to define the loads. Go to define and then load patterns. So these load patterns have already been defined. Dead load as self weight multiplier of 1 and live load as self weight multiplier of 0. It's fine. So press OK. Again go to define and then load cases. Both these dead and live loads have been assigned as linear static load case type. That's OK. Go to load combinations. Here we no combinations have been defined, so we need to define the combination. Go to add new combination and load combination you can give for the first combination as combo 1. Here you can add a dead load and give the scale factor as 1.5 and you can give live load and give the scale factor as 1.5 as well. This is the ultimate load combination. So you can select strength ultimate here and don't tick other options. So go to OK. Combo 1 has been assigned. Again add new combination. You can give name as combo 2. Here dead load will have scale factor of 1 and live load will have scale factor of 1 as well. Okay, and then tick the service initial, service normal and service long term properties. Press OK. So both our combinations have been defined. Okay, now we'll be drawing the mat foundation slab in these grid lines. So go to draw and then draw slabs. Draw slabs. Okay, type of the object is slab and in property, mat footing has already been chosen. So now we'll draw from this point, from 1A. Select here, go to this point and then up to here and again to the starting point. Okay, now our slab has been drawn. This is 18 meter by 18 meter slab we have drawn. Now press escape, select the slab once, 1 areas, 4 edges selected. It can be seen here that we have selected the slab, and what we need to do is we need to expand this slab by 2 meter in x-axis and y-axis. We need to expand a little bit because the columns will come at the ends. So go to, after selecting, go to edit and then go to edit area and then we'll go to expand shrink areas. So offset value we will increase by 2 meters, that is 2000 mm. Okay, our slab has been expanded by 2 meter in x-axis and y-axis. Now we can draw columns in the slab. So go to draw and then go to draw columns. You can check it here. Type of object is column. Property below, in property below you can choose none, and property above will be column 500 by 500. First we will draw all the columns which have dimensions 500 by 500. Height below will be 0 and height above will keep 2 meters. For the 3D view we can see some height of the column, and let us start drawing the columns. Let's start with C1. C1 is here. Yes, our column has been drawn. Now similarly another column of dimension 500 by 500 is C2. So the distance is shown in blue color as 6 meter. Okay, so position of C2 is here. Again in 6 meter value C3 column is there, and again in another 6 meter C4 is here. Now from here the distance in distance 6 meter, this is C5. Now C6 is have dimension of 600 by 600, and C7, which will be here, will also have dimension 600 by 600. So another column will be C8, which will be 6 meter from this column. Yeah, and C9 will have here. Again C10 and C11 will be of different dimension. So go to C12, yeah, and then C13 will be, yeah, C14, C15, and C16. Okay, now we can change the column property as 600 by 600 and give these columns. This is C6, this is C7, this is C10, and this C11. You can see some sizes and difference here. Now we'll be drawing the design strips. So press escape and then go to draw, and then go to draw design strips. So for design strips, first we will draw the strips in layer A, and then we'll start with strip width we had calculated initially as 4 meters. So we'll keep all the values as 4 meters. Now to draw the strip layers, we'll start from the end. Two meters had been added. Now change the strip layer to B, and all the column width will be 4 meter here as well. Okay, you can see the pink lines here. These are the strip lines. Now press escape, and now we'll go to assigning part. So first we'll assign the soil properties. So click on the footing area once. Click on the footing area, one area, 4 edges are selected. So go to assign, and then go to support data, and go to soil properties. So soil 1 has been selected, and we'll assign this soil 1 to the selected slab. Okay, now select this column 1, and then you see the 1 point has been selected. This is C1, and then go to assign, and then we'll be assigning the loads in those columns. So go to load data, and go to point loads. Here first we will assign the dead load and then live load. So we need to see the previous data of live load and dead loads, and we can fill in these data. So first in C1 we have dead load as in gravity minus Z, we have dead load as 1850 kilonewton, and we need to change this dimensions as well of the column. So x dimension is 500 and y dimension is 500. Press OK. Again for this point, one area, go to assign load data, give the load as live load, and the live load is 797.6, dimension is same. Okay, so both dead load and live load has been assigned here. Now we'll go to next column, C2. Press at the center of the column, assign load data, point loads. First dead load, and the dead load for C2 is 3013.3 kilonewton, dimension is same. Okay, again press escape, press the center, assign load data, point loads, live load. Live load is 1437 kilonewton. Okay, similarly for all the columns we'll assign the loads. Now we'll assign loads for C6, C7, and then C10 and C11. We should change the size of the columns in these columns. Dimension is 600 by 600. Now we have assigned load for all the columns. These columns load has not been assigned in this one. Dead load has been assigned. Here I think live load has not been assigned here. This is C10. Six four four. Dead load has been assigned 2 times here, I think. So dead load was 5154. 6. Yes, now it's correct. And we have assigned loads for all the columns. You can see all the columns marked. Now we need to make some changes in the slab properties. So right click on the footing area. In the in the design, in rebar material, you can see that we have to assign rebar as HYST500. Okay, it has been assigned. Okay, now in this design strips, we should right click, and then again in design, this rebar material we should change to HYST500. Okay, so for all the design strips, I mean to right click and then change the rebar properties. Okay, now we have assigned rebar for all the strips and then mat footing. Now assigning part is completed. Now we can analyze the model. So go to run and perform run analysis. We have not saved the file, so we can now save the file. Okay. So our analysis has been completed. This is the displacement shapes, and the displacements in millimeter are given in this scale chart. You can see the displacements. Now again go to run and then run analysis and design. So it has been performed. Now go to now go to display and go to show punching shear design. So here you can see that our punching shear ratios are all above. Some values are above 1 and some values are below 0. So in order to this pass the punching shear, our values should come below 1. So what has happened is our slab dimension is not enough, and then in punching shear it is failing. So now what we need to do is change the slab dimension, slab depth we need to change. So first unlock the model. Okay, and then in our slab properties, modify. Previously we had assigned as 800 mm in trial and error basis. Now this is not enough, so we can increase the slab height thickness as 1200 mm. Okay, okay, now again we need to perform analysis. And then again run analysis and design. Now go to display and now check for the punching shear. Now you can see that all the values are before 1, lesser than 1. So it has passed in punching shear. Now if you want to see some extruded views, you can go here and then in the options you can click to extrude view. Okay, and go to 3D view. So now we can see our 3D view of our mat footing. Again go to this view and then untick the extrude view. Okay, go to XY plane. Now our analysis part is over. just to check our results, you can view many properties. Like you can go to display, and then you can go to show strip forces. Here you can see the moment as well as shear forces. Click on apply. You can see all the we have clicked to moment, so the bending moment you can see in these strips. If you want to see in other layer, you can see in other layer as well. If you want to see the shear force, you can see the shear force diagram. Again, you can go to display and see the show slab design. Click to impose minimum reinforcing and then apply. So here you can see all the minimum reinforcement required in the slab. If you want to see the other layer, you can see in the other layer as well. Also, you can go to display and go to show slab forces. Here to see the maximum moments, you can click to max and then to apply. So these moments you can see here. Also you can see some crack widths also you can see. So go to display and go to show crack widths. In the load case you can vary for the dead load case, and to see the cracks at bottom face or at the top face, you can click here apply. So these are the cracks at the bottom face. As you can see, this color represents here, and these are all in terms of 10 to the power minus 3. So they are very you can see the cracks here 0.107 mm. So these are very small width cracks and doesn't matter. Now finally you can go to run and check the detailings. Go to run and go to run detailing. Click all these properties and press OK. Now our detailing has been completed. At the left side you can go to detailing, and then in drawing component views you can go to slab views and to rebar table. Here you can see all the rebars required, their diameter, shape code, and the cutting length, number of rebars required, and total length of the rebar. Also you can see the rebar schedules and then BOQ, bill of quantity of the rebars. Also in individual slab views you can see our rebar plan. This is the rebar plan required for our mat foundation. Okay, so therefore in the detailing part we can see lots of detailing of the rebar required for our mat foundation, and you can see whatever you like sections and reinforcement profile, etc. By this we come to the end of our design analysis of mat footing. Thank you very much.